Hi, everyone, and welcome back to part two of Missing Data. We are going to pick up right where we left off and actually get into probably the core of what you might be interested in, which is techniques for actually addressing missing data when we're estimating a regression model. Broadly speaking, there are two really good ways: full information, maximum likelihood, and multiple imputation. Both of them work extremely well with missing completely at random data. Now, you may be thinking, oh, you mentioned before that you could use listwise deletion with missing completely at random data, which is true, but we still might want to have a bigger sample size, for example, for power. So, power is basically the probability that you would detect a true effect or true association, assuming there was one. And the bigger your sample size, the more likely that would be true. So generally, we want a bigger sample size. So rather than deleting that data as you would do with listwise deletion, these techniques would actually not just outright delete it, we'd actually use the information we have from cases. So even missing completely at random, there might be a good reason to use these techniques. Broadly, they also really work well with missing at random data. So that's kind of where we just left off, where we presented this case where we had two independent variables that were related to the probability of missing data on our dependent variable. And that was a part of our case for basically arguing for the tenability of assuming missing at random data. Though there are these kind of two main solutions, I'm going to focus on one: full information, maximum likelihood. The basic reason, in my opinion, I think it's the most elegant solution, and I also think it's less prone to user error. I'll be talking about multiple imputation a little bit at the end and how to implement that. But just want to note that why I'm going to be focusing on full information maximum likelihood. Naturally, it has maximum likelihood in the name, so you probably guessed you do need to be using maximum likelihood estimation for your model to be able to use full information maximum likelihood. I think that's honestly not too much of a problem in a lot of cases, as maximum likelihood estimation is often the default estimation routine for a lot of models. Generally, you can use something like ordinary least squares, but I can't really ever really find a really good reason why you would choose that over full information maximum likelihood, though there's probably some particular cases where maybe that would be justified. But for a lot of regression models, especially if you have a decent sample size, maximum likelihood is a good way to go. And it's really easy to implement full information maximum likelihood. And building on what we talked about in the previous videos, you can actually build in addressing missing data and also potential violated assumptions. So, for example, if your data were not multivariate normal, you could address that, for example, get robust standard errors, and also address missing data at the same time. So it's a quite efficient and useful approach, and it's kind of my default, though it's not going to be applicable to every single case, and I'll be talking about multiple imputation a little bit. So I'm going to show how to do this in Lavaan, which is one of my favorite packages to use. So the first part, we're going to do what we did before when we just estimated a regression model using maximum likelihood estimation. So going through those steps, first specifying the model, so regressing y onto our independent variables, and then fitting it with this command here. Though one thing you will see is I've added this command here, missing equals ML. This is specifying that we want to use maximum likelihood, or again, formally full information maximum likelihood, to address the missing data. So Initially, we see that we get this warning here that 54 cases were deleted to missing values in the exogenous variables. Always tough to say that word, but our independent variables. So those ones we're actually handling as list-wise deletion. Again, remember when we're focused on missing data mechanisms, they're specific to the dependent variable. So in this case, we were focused on missing data on our dependent variable. So we're actually deleting the cases that have missing values on our independent variables. Though we'll talk about there are all ways for potentially addressing that if appropriate. So that's just telling us, but just to make this point, even with using some sort of approach to address missing data, you might still be using, listwise to some extent or a version of it. So now let's look at the fit of the model. Main thing I'll point out here is you'll see 446, that we have that sample of 500. What we're actually using for analysis is 446. Again, that's because we deleted those 54. And then we also, as before, when we did the MCAR test, reporting the number of patterns. Here, among the data that we are using, there are two missing data patterns. And we can actually look at those patterns to see what they look like. So here you can see we have those two missing data patterns. And essentially we have one complete data on all our variables and then complete data on only our independent variables. Now, the next thing we want to look at is what's called coverage. So I'll show that real quick. And essentially, you get what looks like a correlation table. And what we're getting here is for each pair of variables, we're getting the proportion of data present. So if it's the same variable, the y to y, that's just how much data is present for the dependent variable. So 75% of data is present. And then you can go in, how about x1 and y? The general rule, again, a heuristic for the kind of coverage you want is basically greater than 50% is what you want to look for. So in this case, again, we have 100% coverage and then 75. Some of the lowest is 75%. So that would be looking good. And generally why this kind of coverage matters and why we would report it. Kind of stepping back a little bit and what we're doing here, what full information maximum likelihood does. Without getting into kind of the complicated math of it, the logic of it is pretty simple. The core idea of it is that we use the partial information, right? So we have some cases, right, with some incomplete data on, like our dependent variable, but they have information on the other variables. So the basic idea is that we use that partial information in our overall estimation routine. So we don't outright delete it. It's not what we might call kind of a complete information, like a complete full data, but it provides some information and we can still use that. So generally, you can think about this as kind of like a proportion, kind of pairwise, the amount of information that we have on variable by variable. So the univariate, but then also bivariate as well. So why we want more than 50% is we want a decent chunk. Yeah, we're going to use this partial information, incomplete information, but we still want a decent amount of it. That's kind of the basic idea of what we are doing. Now, as I mentioned, you can incorporate a robust approach. So before we had talked about using or estimating robust standard errors if you have heteroscedasticity. So that's something that we could incorporate here when we have missing data and we also want to estimate robust standard errors. So here we see that again, sandwich errors. We just added in that estimator MLR here. So that's incorporating what we had did previously when we were talking about addressing heteroscedasticity. And then we just added this missing part. So that's why I mentioned again why I think it's a really useful approach, because it can be a real nice kind of one-stop shop for addressing missing data and things like departures from multivariate normality. Now, one point to return to briefly. So we deleted all the cases that had missing values on all the independent variables. Well, it's actually, in principle, possible not to delete them. And what we could actually do essentially is estimate the sample descriptive statistics. Um, you would not want to do this, what we're about to do here, unless your data were MCAR. So if you felt confident about that and had evidence to support that case, this would be appropriate. But generally, in this specific case where we argued for missing at random data, independent variables are related to probability of missing data on a dependent variable, we would not want to do this in this case. But I just want to show you this approach. And the command is just saying fixed x is false. Or in other words, we're not using our sample statistics. We're actually estimating them as part of the model. So now you'll see when we get the full model, now we're actually getting more things. Now let's do a little bit more digging. Now we see lots of more patterns as well. Again, we are not deleting all those cases that had missing values on independent variables. And now we have a lot more patterns. And now it matches actually what we saw when we did the Little's MCAR test. We actually have 9 overall patterns of missing data. And now if we look at coverage, we also see that we get some variation, a little bit difference compared to last time. So now the core of it, again, what we're doing, rather using the sample statistics, we're actually estimating the sample statistics as part of the model, which actually allows us to incorporate even more of that partial information and actually get the sample size for this part would actually be the full 500. Again, you want to make sure this would be appropriate to use in your specific case, but I think it's a nice kind of illustration of the idea of basically just don't use listwise deletion. Rarely are there really good reasons just to outright delete your data. You can still incorporate generally or account in some way, have that bigger sample size, greater power, and ideally have also unbiased estimates. Now, in every case, full information maximum likelihood might not be appropriate or the best route. The other best approach for handling missing data is called multiple imputation. And I just kind of want to run through the basics of it. But this is one I think, in principle, I'm not opposed to it, but there is a lot of room for what we might call kind of user error here. And first, you're going to need some more packages. So you're going to want to install these first, mice and some tools. And here I'm going to do a relatively straightforward, simple way using the Lavon package. So instead of using full information maximum likelihood, we're going to use multiple imputation. And I'll just run through it and then I'll kind of talk through the basic steps of what's involved. But you can see here just a slightly different kind of command we have going on, and I'll explain these parts. But basically, we have to call this other package to do the actual multiple imputations for us and then send it back to Lavon is basically what happens here. So I'm just going to estimate this first and then I will talk about it. So first thing to point out, the results are approximately the same as full information maximum likelihood, which would be generally true. If they're both going to be appropriate options and you kind of use them appropriately, then you're probably going to have quite similar results. But the basic idea of multiple imputation is that we generate plausible values for the values that we have missing. So you generate them, right? And then we could potentially have a full, complete data set after we add them in, right? So then we can estimate a model. And then basically we do that multiple times, or it says M times. Typically, the kind of default is 5. You might do upwards of 10. And then you basically pull the estimates from across all those models according to Rubin's rules, they're called. But basically, it's just a way of pulling all the estimates so you get one overall estimate. So just based on my description there, you can see that there's lots of steps involved. Again, it's not a bad approach. That can actually have lots of advantages for you. In my mind, one of the trickiest parts, though, is you really need to have a good rationale behind how you're generating those plausible values. In this case, what we did is the defaults, which specifically uses, it's called Gibbs sampling. I'll talk about a little bit of related things in videos, probably that are a little bit down the line at this point. But essentially, we're simulating values here, just based on probability and the distributions of our variables. So generally, you can say, yeah, that's okay, but depending on specific kind of circumstances of what you're looking at, now my dogs are barking in the background. Depending on your specific circumstances, there might be a different approach. You can actually design an entirely custom function for generating those plausible values. So it really comes down to that rationale. And as I mentioned, there's lots of steps involved, which in my mind makes it a little bit more likely that you could make a little small mistake here or there, and in turn, maybe have problematic results. But again, it is a really good strategy to use. But in my opinion, I tend to go with the full information maximum likelihood when I'm doing regression models and want to address missing data, and also often address things like heteroscedasticity. So I hope this video was valuable and useful to you. And thank you for watching. And I'll hope to see you in the next videos that we have coming up. See you there.